And guys, today what we're going to do is we are going to talk about all of the things that are true because intermolecular forces exist. Now guys, are y'all caught up? I know this isn't what you were expecting, and some of you are sort of skating, trying to catch up. You guys ready to roll? Is that okay? Understanding that the drawback to not grading the homework is you don't have that connecting point. Are you okay? Intermolecular forces, dipole-dipole, hydrogen forces. Now we're going to talk about so what. So guys, the conversation goes like this, and let me just tell you, and maybe I didn't mention this to you, I don't know. Did we talk about what these questions look like on the AP test? We didn't? Okay. So, well, you'll see. The test that we have on Friday, I will offer up to you a selection of these questions, of course. But guys, the bottom line is this. These questions, the things that we're going to go over today, are the questions that students score the worst on every year. The scores on these are typically in the 40% range on average. So typically people get like 3.5 to 4 points on average out of 9 on these questions. These tend to be difficult. The problem is this, so let me just lay it out for you this way. Guys, in order to be able to think through the things that we're going to talk about today, and a lot of it's going to be review from last year, you've got to use the word therefore. Guys, this is all cause and effect reasoning. And frankly, guys, I've always assumed that my students are good at cause and effect reasoning. I'm finding that's not the case. So actually, this year in general chemistry, I'm teaching cause and effect thinking just to make sure we understand how that goes. But guys, the bottom line is this. When you're going through this material, doing homework, answering questions on the test, guys, you've got to be thinking, this is true, therefore this is true, therefore this is true. So guys, that word therefore, if you don't find yourself writing down the word therefore a lot, you're probably not approaching this correctly. So guys, here's what we're going to do. We understand that intermolecular forces exist. We understand that they exist because there's polar molecules. Guys, what we're going to do today is we are going to talk about all the things that are true of substances because polarity exists and therefore intermolecular forces exist. So guys, we're just going to go through the laundry list. Some of this is review from last year. Some of this is new this year. The stuff that's review, feel free to slow me down if you need. The stuff that is not review, I will spend time and help you make sense of. Then guys, when we're done with that, here, let me pull this down. When we're done with all of this phase stuff, then guys, what we're going to do is we are going to look at what are called phase diagrams, something we haven't looked at before. And then we're going to talk briefly about the properties of solids, but this will largely be just something, it's a page and a half in the book that you just need to read. So, you ready to go? All right, first things first. So guys, the first of the characteristic properties that we need to review, and the ones that we're going to talk about primarily have to do with liquids. Guys, before we talk about them in order, we need to make sure that we have sort of a mental picture of how intermolecular forces work. So if you picture it like this, and if you picture that this is a beaker that contains a liquid, this is not a bad representation of intermolecular forces. The molecules that are at the surface are being drawn downwards. The molecules that are contained within the liquid below the surface are being pulled in all directions by these forces that exist between the molecules because they're polar. So guys, first of all, viscosity. So we're going to go through these as sort of a laundry list, and we're going to talk about what are the relationships between intermolecular forces and these properties. So guys, we'll define them first. Do you know what viscosity is? Yeah, exactly. It's the thickness of a liquid. So guys, it's technically defined as this. It is the resistance of a liquid to flow. So water has a relatively low viscosity and syrup has a relatively high viscosity. So it's basically how goopy something is. Do you guys know how they measure viscosity? Yes. Do you guys know how they do it? They actually do it with a stopwatch. It's interesting. They take a large, and I don't think it's called a viscosometer, but they actually have a standard tube and a standard round mass. And what you do is you release the mass into the liquid, and then you time how long it takes to get to the bottom of the tube. And obviously, the longer the time, the greater the viscosity of the liquid. So guys, the question then becomes this. And I'm not going to give you this in notes, you just need to include this in your notes. What is the relationship between viscosity and intermolecular forces? Is it a direct or an inverse relationship? Direct relationship. So guys, let's say it this way. The stronger the intermolecular forces, the more viscous the liquid. Which means you should immediately have a problem with water. Because guys, water is wildly polar, hydrogen bonding, right? So what do you know about the intermolecular forces in water? Crazy strong. But what about the viscosity of water? It flows like water, right? Do you see the problem? So guys, we've got a substance that we know to be highly polar, therefore the intermolecular forces are strong. You just said it's a direct relationship between intermolecular forces and viscosity, which would seem to violate our idea here because we have a highly polar liquid with a very low viscosity. Why would that be true? What is it about water that makes that true? Say it again. It's itty bitty. Guys, that's the other factor that plays into this is the size of the particles. And water is so small that it doesn't have a problem getting out of the way, and therefore it actually flows very readily, unlike something like syrup, which is sugar, or oil, which are long-chain hydrocarbons. Guys, those are big elongated molecules, and even though their intermolecular forces are lower, they are so big that they have a hard time getting out of their own way. So you may want to mention something about size is also a significant factor in predicting viscosity. But it doesn't negate the fact that it is directly related to intermolecular forces. So if you have two molecules with approximately the same size and mass, the one that's more polar will be more viscous. You guys good on viscosity? Okay, the next two we've done before. Adhesive and cohesive forces. We did this last year. Guys, adhesive forces are the forces that bind one substance to another, sometimes a surface. We can just say to another. That might be a better way to put it. I like that better. It doesn't have to be a surface. So guys, an adhesive force binds one surface substance to another. This is what causes the meniscus. And then cohesive forces are forces within the substance. And this is what causes things like the surface tension that you get with things like water. Again, guys, that's all review, so I felt comfortable rocketing through it fairly quickly. The next one that we're going to do is not review. And so we're going to have to spend a little more time on it. So guys, now we need to relate this to intermolecular forces. So will the adhesive forces and the cohesive forces of a substance be directly related to intermolecular forces or inversely related to intermolecular forces? Directly related. So the more polar the molecule, the stronger the intermolecular forces, the more adhesive that substance will be, and the more cohesive that substance will also be. That's why, like, water has such a strong cohesive force that bugs can walk on it, right? You see the little water striders that can walk around on the surface of a still pond? Guys, that's why. And you all, of course, know how to kill those bugs, right? Yeah, just put a drop of soap on the water, and soap contains something called a surfactant that breaks the intermolecular forces, breaks the surface tension of the water. The surface tension fails, and all the bugs drop to the bottom and drown. Yeah. What's that? Yeah, so So we'll talk about it just a little bit. So soap is a magic substance because soap actually has an end that is very polar and an end that is very nonpolar. Now, we haven't talked about solubility, so this may not make a lot of sense. But you find out that most dirt is nonpolar, oil, grease, things like that. It's nonpolar. And so what happens is soap actually, it kind of works like a bridge. So soap molecules have got one end that's very polar and water's attracted to it. And then it's got another end that's very nonpolar that oils are attracted to. And we'll find out that nonpolar attracts nonpolar. We'll talk about why on Wednesday. But the idea is that what soap does, it allows a polar water molecule to grab a hold of nonpolar dirt because it sort of acts as the intermediary that attaches to both. That same property also allows the soap to grab a hold of the water molecules, keeping them from attracting one another. And when that happens, the surface tension breaks and the bugs die. So, yeah. So, Google soap molecules and take a look at what they look like. They look like these long snaky things with a polar end and a big long non-polar end. Kind of interesting. We'll look at it next time. So guys, you good on adhesive and cohesive forces? Because we're about to get into one that's new and a little bit tricky. You ready to go? Okay. And guys, this one is actually the one that they love to pick at on the AP test. We didn't talk about this last year, frankly, because most general chemistry students can't wrap their heads around this. But you all should be able to. So guys, the thing that we need to talk about is what is called vapor pressure. So let me define it for you. Guys, vapor pressure is the pressure of a gas that is supported over a liquid. So let me draw for you what that means. Maybe. Let's try. So guys, and I think you're probably going to benefit most from drawing this with me. Really, it's most easily understood if you look at it graphically by trying to scratch a picture. Then what I'll do is I'll give you words to describe what you drew, and then we'll put it in motion with one of the most worthless videos that our book actually offers up, but we'll watch the first 12 seconds of it and you'll see what's going on. So guys, do this. Draw yourselves a beaker. Now put a lid on your beaker. Now put some water in your beaker. Like so. Now guys, take your picture and turn it into a video. What are those water molecules doing in the liquid phase? They're running into each other, they're running into the walls, they're going crazy. What happens to them when they get to the surface? If they have enough energy, they will break out of the surface of the liquid and they will go into the vapor phase. And guys, what do we call that process? Evaporation, right? They will in fact evaporate. Realize that in order to evaporate, they've got to break the intermolecular forces that hold them back. And by the way, guys, what do we call the measure of a substance's ability to evaporate? Do you remember from last year? Volatility. Okay, so with that, now we've got some of these molecules up here chilling in the gas phase. But now, guys, playing your video, what are these gas phase molecules doing? Same thing, running in straight lines, running into each other. Sometimes they run into the surface of the liquid. And when they run into the surface of the liquid, what could happen to them? They could stick and not evaporate, but what's the opposite called? Condense, right? They go through condensation. Now, guys, what do you suppose is going to happen as this liquid is evaporating all the while the gas is condensing? It will reach equilibrium. And guys, the pressure that is exerted by the gas over the liquid is the vapor pressure. Now guys, here's the thing that makes this interesting. The vapor pressure is attributed to the liquid. So we would say the vapor pressure of the water is then whatever the pressure is of the gas. But we attribute the vapor pressure to the liquid. So those are the fundamentals of vapor pressure. You get it? Now let's do this. What do we do to this water in order to change the vapor pressure? Say we want to make the vapor pressure higher. Heat it up, right? So if we add heat to the water, then the molecules are moving faster. More of them have enough energy to break the intermolecular forces and escape. And likewise, the particles that are hitting the surface of the liquid, it takes a greater release of energy for them to stick. So consequently, you'd have more particles up here in the vapor phase. Oh, that almost looks like a solid, but you get the idea, right? You've got more particles in the vapor phase, thereby increasing the pressure. So we now understand what vapor phase is, or vapor pressure, and we understand that vapor pressure is dependent upon temperature. You good on that? Okay, so now what if we do this? Let's clear this up. And now guys, what if we bring in, so this is water, and well, you get the idea, right? And then let's bring in methanol. Remember when we did this last year? So now we're going to bring in some CH3OH particles. And guys, same deal, right? These are jumping into the vapor phase. These are being captured. These are jumping into the vapor phase. These are being captured. So guys, if these things are at the same temperature, will their vapor pressures be the same? Why not? Relate it back using therefores. How does it work? Someone want to take a swing at it? Go ahead, Spencer.
So, water has higher IMFs than methanol.
Okay.
Or water will have a lower vapor pressure. I mean,
No, you were right. Keep going.
Lower vapor pressure.
Yes.
Than methanol.
Good. So guys, what is the relationship between intermolecular force and vapor pressure, direct or inverse? Inverse. You want to write that down. This is inversely related to intermolecular force. Now, I think Spencer did a great job of describing that, but guys, understand that if the question on the test were which one at equal temperatures, which has a greater vapor pressure, water or methanol, sadly, he wouldn't have received credit for the answer. Didn't mention. No, he said it was less, but what big idea didn't he mention? Polarity. Guys, when you are answering these questions, you have to map them all back to polarity. So there was one statement that needed to come first. Water molecules are more polar than methanol molecules. Therefore, water molecules exhibit greater intermolecular forces, stronger intermolecular forces. Therefore, water would have a lower vapor pressure than methanol. So guys, bottom line is this, and I'm actually glad that Spencer did skip mentioning that because it helped us highlight the idea. Guys, you've got to map every single one of these back to polarity and then do the therefores. And then Gavin brought up a good point as well. Be sure that you're mentioning both substances because you're going to see on the test, guys, and in homework, a lot of these are comparative. This dissolves in this while this doesn't. This has a greater vapor pressure than that. You're going to see a lot of comparative stuff, and as Gavin reminded us, you've got to mention both. It isn't enough to just mention one or the other. You groovy? Okay, so guys, this then would be the summary. Please be judicious in what you write down. You've already got this, right? The vapor pressure of a gas is indirectly related to the IMFs within the liquid. We understand that higher intermolecular forces means more energy is needed for these things to escape. Therefore, they have lower vapor pressures. You good? I think you've got all that, right? Yep. Isn't that right? Or do you like inversely better?
Indirectly, it kind of sounds like it's, affecting it. Like,
Oh, I always think of those as being the same. Is this better? Okay, I'm more, you would know more about that than me because you guys are more mathematically attuned right now. Is that better? Inversely? Is that better? Okay. So guys, let's do this then. Let's add one additional thought to this and really bring this home. Guys, thinking about the relationship then between methanol and water, which would have a higher boiling point? So think about it. Water has stronger intermolecular forces, therefore more energy is needed for it to escape, therefore it has a lower boiling point, therefore what will be true, or I'm sorry, a lower vapor pressure, therefore what will be true of its boiling point? It'll be higher. Yeah, so guys, the relationship here then is that these things have higher boiling points. So you don't have to go vapor pressure to get to boiling point, but that will always be true. Substances that have low vapor pressures will have high boiling points. Water being a great example. Yeah.
So the boiling point is when the vapor pressure is equal to 1
Atmospheric pressure, whatever it is. I mean, here it's lower, but that's exactly it. Guys, did you make that connection that Everett just pulled together? What was that, like Appendix B or something like that? Where was the appendix where we got B, which I can never find? But let's make that connection because it's at least interesting to me that if you come back, guys, to Appendix B, down here, right, we have this table of vapor pressures for water, and you find out thinking about like, is that it? Vapor pressure of water. Yeah, and so you find out that the vapor pressure of water is 760 at 100 Celsius. And so that's the idea, is that now that we understand vapor pressure, we understand that the pressure pushing up is equal to the pressure pushing down, and that's the point at which it boils. Yep. You guys bring that all together? Does that sit okay for you? Is that good? Okay. All right. So guys, with that said, the world's most disappointing video bundled with our book. You ready? Here we go. Vapor pressure versus temperature. So what is the relationship between vapor pressure and temperature? Temperature goes up, vapor pressure goes up. You ready? This is as good as it gets. Here's a thermometer, here's a pressure gauge. Here's a heater. You know what? I want to hear the audio. I've never really listened to the audio, and I can't imagine what they're saying because this is boring.
A liquid confined to a cylinder, as shown here, with no other substances present, exerts a vapor pressure in the space above it. Molecules continuously transfer back and forth
All right, there's our equilibrium.
between the gas and liquid phases. The gas pressure in the cylinder represents the vapor pressure of the liquid that results from this equilibrium.
Did you notice how she said that, though? The vapor pressure of the liquid. Maybe I should have listened to the audio. This isn't as bad as I thought. So the vapor pressure of the liquid. And guys, that's important when you're describing this. It's the vapor pressure of the liquid. We attribute it to the liquid.
As the temperature of the cylinder increases, the average kinetic energy of the molecules increases in both the liquid and gas phases.
Get it? So guys, the thought here being, molecules moving faster, more likely to be in the vapor phase, pressure goes up. You good? Good stuff. All right, moving along. So we're now done with vapor pressure. What about volatility? Do we even need to talk about it? You okay on volatility? Do you remember what it was? Let's define it just in case. So guys, volatility is its ability to evaporate, and I think we're okay with the connection that if you have liquids with high vapor pressures, they evaporate more readily, and we understand this to be therefore a volatile substance. See, I think some of you may think that volatile means explosive. And guys, understand that that's also a related idea. We use the term to mean that as well, simply because if you've got something like gasoline, actually when gasoline explodes, it's not the liquid, it's actually the vapor that's catching on fire. So something that vaporizes readily, if it's flammable, will also be explosive. You guys know that, right? You can put out a match in gasoline. Please don't try this, but you can look it up. You actually can. If you've got a fan blowing across the surface of a cup of gas, so long as you don't have vapor building up, you can actually take a lit match and put it out in a cup of gas. It won't catch on fire. Yeah. So long as there's... Okay, so this is recording. Do not go home and try that. Look it up on YouTube where someone else risked their life. And then guys, that's right. And then guys, finally boiling point. We understand the boiling point as, and this is exactly what Everett said, but we can actually now define it technically. The boiling point then is the temperature at which the vapor pressure of a liquid equals the pressure being exerted on it. And it's at that point that this molecule or this system does not reach equilibrium and it just boils dry. But then guys, relating this back to intermolecular forces, the stronger the intermolecular forces, the higher the boiling point. Go ahead. Yeah. So realize that this begs the idea that the gas can escape, right? The vapor can escape. So if we put a lid on it, you have a feedback loop, right? So the water is boiling, creating a vapor, which then creates a pressure, which pushes back on the water. And we understand that as the pressure goes up, the boiling point goes up, and it's like chasing its own tail. Yeah, so eventually something's got to give. But yeah, you're absolutely right. Right, or it's why you don't screw the lid off of the radiator in your car, because you've got water in your radiator at like 120 Celsius because of the pressure pushing on it allows it to exist as a liquid at that temperature. And the minute you screw that lid off, the pressure drops below the boiling point, that thing flash boils and you're in a lot of trouble. Yeah, precisely, yeah. Yeah, so regardless of where, yes, the heat can also be lost to the surroundings, right? But for that molecule in this, so here's our water, right? Here's the surface of the water. And for that molecule to hit and stick, it has to release energy. Some of that energy can go back into the liquid, causing others to boil. Some of it's radiated into the surroundings. But yeah, absolutely, it has to lose energy for it to re-adhere, if you will. Yeah. You guys good on all of this? Okay. So guys, we're done with all of the things that you need to understand. Well, that's not completely true. Solubility on Wednesday. Guys, on Wednesday, we're going to talk about why things dissolve in what. But we're done with all the physical properties of substances that you need to understand relative to intermolecular forces. So what we're going to do now to wrap up the day is we're going to look at phase diagrams. Now, guys, you've never done this before with me. I doubt you've, well, let me just throw one up maybe and see. Did you ever look at these in physics? No? Okay. Maybe the triple point rings a bell. So guys, this is what we're going to do to wrap up the day. This is a phase diagram. And by the end of the day today, you are going to learn to interpret these diagrams and also use these diagrams in a predictive way to talk about how changing the environmental conditions of a substance will cause it to change phase, which makes sense because these are phase diagrams. Now guys, fundamentally from a distance, and we're going to spend a lot of time with this, you'll notice that the x-axis is temperature. The origin of the graph is 0 on both axes. The Y value is pressure, doesn't matter the units, so long as you understand that this is a vacuum at absolute zero. Get it? No stuff, no heat. So it is a vacuum at absolute zero. This then would be really hot and no pressure. This would be really high pressure and no heat. So the idea is that as you go up or out from the origin on either axis, these values are increasing. So guys, don't write this stuff down. Just play along, you'll see. So guys, fundamentally then, a phase diagram is just a graphical way for us to understand the pressure temperature conditions at which substances will be solids, liquids, and gases. But as I said, we can also use it in a predictive sense in order to figure out how will substances change as they are either being heated or cooled or compressed or the pressure is let off. So guys, we are going to use these in both ways. So what I'm going to do is I'm going to offer this to you visually in a video and allow the video to introduce you to the ideas, and then we're going to go back and unpack those things, and you're actually going to be drawing phase diagrams because you will be drawing these on the test and the AP test. So here's sort of your overview coming at you.
A phase diagram indicates the temperature and pressure conditions under which a substance is a solid, a liquid, or a gas.
So guys, let's just think about that. Notice they didn't give us units. So what's the x-axis? Temperature. What's the y-axis? Pressure. So does this make sense in your head that the solids are on the left, the liquids are in the middle, and then the gases are predominantly on the right? On the x-axis, what is this temperature? Absolute zero. And then we're getting hotter. And guys, we understand that in general, solids are cold, liquids are in the middle, gases are at high temperature, right? That's the way we fundamentally think about it. So guys, when you're asked to label a phase diagram, solid, liquid, and gas, all that you probably need to do conceptually is come back to temperature and think, as I go from cold to hot, they go solid, liquid, gas, with the understanding that some interesting things happen down here. At very low pressures, you can cool a gas down pretty cold and it will not liquefy or solidify. We'll talk about that more later. But the general trend is solid, liquid, gas from cold to hot. Yeah. Mm-hmm. We'll talk about it. It's what it, well, we'll talk about it. It's what is called a supercritical fluid. You'll see.
The lines that separate the phases are called phase boundaries.
Now guys, what do these phase boundaries represent? Phase changes.
At any point along a phase boundary, the phases exist in equilibrium with one another. For example, in the phase diagram of water, at 1 atmosphere of pressure and 100 degrees Celsius, liquid water and water vapor exist in equilibrium. This point is known as the normal boiling point of water.
And guys, normal means 1 atmosphere of pressure.
Likewise, the temperature at which solid and liquid water are in equilibrium at 1 atmosphere of pressure is known as the normal melting point. The point at which all 3 phase boundaries come together is known as the triple point. This corresponds to the temperature and pressure combination at which all 3 phases of a substance exist simultaneously.
Now guys, what would that look like? This is an interesting new idea. So hopefully you understood that these phase boundaries are phase changes. And they gave us, for example, the normal boiling point, which is 1 atmosphere of pressure. It's 100 degrees Celsius. And if you have water at 1 atmosphere of pressure and 100 degrees Celsius, it is both boiling and condensing at the same time. It can move in either direction. It's at equilibrium. Well, guys, down here at this magic point called the triple point, the solid, liquid, and gas phases are all in equilibrium with each other. Now, first of all, notice where that happens, guys. That happens at 98/10,000ths of a degree Celsius, right around zero. And understand that's Celsius and not Fahrenheit. In Fahrenheit, it would be 32 point something very small. So it's not a ridiculously low temperature. It's colder than this right now outside. But look at the pressure. That is not atmospheres. That's 4.58 torr. What is 1 atmosphere of pressure in torr? 760. So guys, that is really stinking close to a perfect vacuum. But at these conditions, water is at its triple point. What would that look like? It would be freezing, melting, boiling, sublimating, depositing. What else did we forget? There were two. It's doing them all at the same time. And guys, if you left it there and came back in a week, it wouldn't look any different. But what would it look like? It'd look like a cup of boiling ice water. It really would. But guys, you would have all three of those substances interchanging simultaneously. Not substances, but phases. Interchanging simultaneously, so the amount of ice, the amount of liquid water, and the amount of steam would not be changing. They would all be interconverting simultaneously, and there would be no net change regardless of time. And it would look like a cup of boiling ice water. Yeah. Whatever you started with. Yeah, whatever you started with is what you'd end up with. It wouldn't change once you got to that point. Yeah. No, they don't. I've never seen one. I mean, I would assume there's one. I've never thought to look, but Google it and see. Yeah. Not our lab. The problem, we actually do have a vacuum pump in lab, and it will not draw down to 4.5 torr. It leaks more than that. But as Everett was saying, certainly we could somewhere. It would be interesting to see what the container looked like, because at 4.58 torr, the pressure from the outside on this would be staggering. It'd have to be a pretty tough container. Be interesting to see. Yeah, sure. Then you could do it no problem. Yeah. So guys, you good on triple point? Okay, let's keep moving.
Equilibrium. When a sample of...
Okay guys, now let's predict. Now we have liquid water. Well, we have water. It's at 1 atmosphere. But guys, notice the temperature is below 0. What happens when we heat it? You understand experientially what happens when you take, so we're below 0, so this is ice, right? What's going to happen when we heat it? First it will melt, then it will liquefy, and then if we continue to heat it, it will boil. What will that look like in terms of what this dot does? It's going to move to the right.
Solid water or ice at 1 atmosphere of pressure is heated, it will melt when the normal melting point, 0 degrees Celsius, is reached. At this point, water crosses the solid-liquid phase boundary. If the sample is heated further, the liquid water's temperature will increase until it reaches the normal boiling point, 100 degrees Celsius. It will then vaporize, crossing the liquid-gas phase boundary. Once the liquid is all vaporized, the temperature of the water vapor will increase as more heat is added.
See how we use that predictively? And guys, those are the things that you've got to be able to talk about. And so some of you right now are going, duh, I understand that if I take ice and if I heat it, it's going to melt, then heat, then boil, then gas. But guys, what if we drop the temperature below the triple point? And what if we heat that? If we drop the pressure below the triple point and then we heat the solid, what's going to happen? Doesn't go through a liquid phase, it goes straight to gas, which we call what? Sublimation. So what do you now know must be true of the triple point of carbon dioxide in terms of pressure? The triple point for carbon dioxide in terms of pressure has got to be what? Greater than 1 atmosphere, right? So guys, if this were the phase diagram for carbon dioxide, the triple point has got to be above 1 atmosphere, because we know at 1 atmosphere, carbon dioxide does not melt, it sublimates, which tells us that this point has got to be above the pressure that exists around us, because if it was lower, it would exist in a liquid phase at this pressure. Yeah. Yes. Yeah, we'll go with that. Yeah, go ahead.
So, does that mean that we could look at the top of boiling ice from the outside?
We can look. I'll pull up the phase diagram for carbon dioxide in a minute. I don't know if we can accomplish the temperatures. We'll look at it in a minute, but maybe. Here we go.
If a sample of solid water is heated at a pressure below the triple point, it will sublime rather than melt as the temperature increases, because the only phase boundary it will cross is that between the solid and vapor phases.
You good with that idea? So now we're at a pressure below the pressure of the triple point, and it sublimates.
We can also track the changes in a sample of water as we vary pressure. If the pressure is increased,
So guys, what's going to happen now if we increase pressure? So we're up at 110 Celsius, and this is existing as a gas. Of course, if we were 1 atmosphere, it would still be a gas. But what happens if we increase the pressure on this gas without changing temperature? What will happen? It will liquefy. And I already showed you. I was going to ask you which direction the dot's going to move, but I showed you with my finger.
on a sample of water vapor at 110 degrees Celsius, it will condense as it crosses the gas-liquid phase boundary.
Now guys, what about this tricky bit? Now we have solid ice. We are at half a degree below 0 Celsius, so like 31 degrees Fahrenheit. Not terribly cold. But the question is this: what happens if we increase the pressure on that solid ice? Which way will the dot move as we increase pressure? Up. What phase boundary will it cross? The solid to liquid phase boundary, and what will it do? It will melt. So what we're saying, guys,
Note that a sample of solid water or ice at a temperature slightly below the normal melting point will cross the solid-liquid phase boundary and melt as pressure is increased.
now guys, why is this? Why is it that ice melts when it's squeezed? Because it's the only substance on Earth that does.
Is it that the pressure will eventually be so strong it will break?
It's actually not. And all other substances on Earth, guys, freeze when squeezed. If you take a liquid of any substance other than water and squeeze it, it freezes. Water is the only substance on Earth that when you squeeze it, it melts. Why? What does it do when it freezes? It expands. See, guys, when water freezes, it expands. Why does it expand? Because water is an itty-bitty, teeny-tiny little molecule that is very polar. And when these molecules lock together into a crystal lattice that makes it a solid, we call it ice, there's a bunch of empty space inside of this crystal structure, and as a result, this thing expands when it freezes. So if something expands when it freezes, what's going to happen if we try to squeeze it? It's going to contract and melt. And guys, water is the only substance on Earth that does that, because water is the only substance on Earth, except for some really obscure things like plutonium. Plutonium also expands when it freezes. But in terms of the things that we actually run into in daily life, guys, water is the only substance that expands when it freezes. Consequently, we can see that when we take solid water, ice, and squeeze it, it melts. Guys, everything else, if you will, becomes more frozen. So you ready for a big thought? If this was the phase diagram for any substance other than water, how would it fundamentally be different? Yeah, the slope of this line would be positive and not negative. Guys, water is the only abundant substance, well, besides plutonium and things like that. Guys, water is the only substance that has a negative slope for its solid liquid phase boundary. Imagine if it had a positive slope and you squeezed it. This would be tipping away and you'd have to heat it more to get it to melt, because all other substances contract when they freeze, and consequently squeezing them makes them more likely a solid. With water, because it expands when you squeeze it, it's more likely a liquid. Yeah? True. Correct. It becomes less dense. Yeah. Absolutely. Yeah. Yeah. I mean, I wonder if an example that pops into my mind, because I'm about to do the lab with my general chemistry kids. Remember last year when we did that phase change lab and you guys had test tubes full of wax and you melted it and then do you remember that? Anyway, I know that in one of my classes we broke so many test tubes that I had to melt a beaker of wax to fill some more test tubes. And so it's the first example that popped into my mind, that I had a beaker full of molten wax, and then when you put in another chunk of wax, it sinks right to the bottom. Yeah, every other substance but water, its solid, sinks in its liquid. Again, it's the size and the polarity. Because water is so small and because of its bent molecular geometry and high polarity, when it packs together, and we don't have to do this, thank goodness, anymore in AP and talk about close packing models, but the closest that water molecules can get together to limit repulsion and increase attraction is into a structure like this that creates a bunch of empty space. Yeah?
So, why then is it plutonium?
I don't know. I just looked it up. I'm not sure. Feel free to look it up, but I don't know. It must be about polarity and size. But guys, it does bring up an interesting point. What you're going to find at the end of the day today is I'm going to give you a little reading assignment in chapter 12. It's literally a page and a half. It's all about the different types of solids, including things like plutonium, which is a metal. Here's the thing. Don't overread this assignment, please. You only need to read 1.5 pages. If you go beyond that, your brain's going to go poof, because it's all about close packing models and unit cells and all of these things that explain why water does this and salt does that and everything else. They wrote it out of the AP curriculum. We don't have to teach it anymore. You're welcome to read it if you want, but you won't see it on the test. So, guys, do you understand the idea then with water having the negative? You're good? Okay. So let's let this continue.
This is one of water's unusual properties.
Unusual properties.
The critical temperature is the temperature
Here you go, Eliza. The blank space. You ready?
above which a gas cannot be liquefied regardless of the amount of pressure applied.
Let me play that again.
The critical temperature is
So guys, this right here represents the critical temperature where that line stops. So listen close.
usual properties. The critical temperature is the temperature above which a gas cannot be liquefied regardless of the amount of pressure applied.
So let that sink in. The critical temperature, the point where this stops, is the point where a gas cannot be liquefied no matter how much pressure you put on it. So you eventually get to this point, and you'll notice that it's the gas phase that sort of leaks up into here, although you'll find out we actually call it a fluid and not a gas. But guys, this phase up here is a substance that is so stinking hot that no matter how hard you squeeze it, you can't get it to liquefy. It's another phase of matter.
The critical pressure is the pressure necessary to liquefy a gas at the critical temperature. The critical point is defined by the critical temperature and the critical pressure. Note that there is no phase boundary beyond the critical point.
Oh,
A substance in this region is known as a supercritical fluid.
okay, so guys, that's where we can stop and talk. So the idea is this. There comes a temperature at which, above that, you cannot get the gas to turn into a liquid no matter how hard you squeeze it. So what we have up here is the fourth phase of matter, which is called a supercritical fluid. It has the properties of both a liquid and a gas simultaneously. So you think about this and you're like, this sounds like something that they put in like the warp drive of the Enterprise to get it into warp speed to go visit the Klingons, right? Guys, here's the thing. These things actually have industrial applications. The one that's near and dear to my heart is actually they use supercritical carbon dioxide to decaffeinate coffee. It turns out that if you take supercritical carbon dioxide, and we'll look at the temperature pressure conditions in a minute, it actually kind of does behave like a liquid. And when you soak coffee beans in it, the caffeine in the coffee beans is actually soluble in the supercritical carbon dioxide. So they soak the coffee beans in it, then they take the coffee beans out and all the caffeine is left behind in the supercritical carbon dioxide, and then they can actually decrease the temperature and the stuff just vaporizes and you end up with the caffeine left behind. So they can actually use something like this in a very real industrial environment. Is it germane to what we're doing? Go ahead.
I was wondering, I noticed that on this picture, and I don't know how accurate the picture is, I'm assuming it's accurate, the supercritical fluid line kind of curves in, so it gives the appearance that if you continue adding pressure to a liquid, it would eventually become supercritical. Can you see it?
Oh, you mean this?
Yeah.
No, don't read any. It's just, again, this is an animation versus a simulation, right? And this is clearly an animation. It doesn't do that. Yeah. I don't know that there's an answer to that. I would think that for gases it could be quite low. We'll look at another example in a minute and compare to carbon dioxide. So guys, bottom line is this. Big ideas. Down here, no pressure, no temperature. What is this? The triple point where all three phases exist simultaneously. This is the critical point above which you cannot liquefy a gas no matter how hard you squeeze it. And that phase that exists above that is a supercritical fluid. Exactly. No, some of it, well, I don't know. No, it can't. You can't do that because think about, Jason, that's interesting because that couldn't be. Because if you had a gas, you'd be somewhere in this region, and in taking it to that point, some would have to freeze and some would have to liquefy. So when you hit that point, you'd have to have all three phases because you can't just magically go there. You've got to get there, and in getting there, you would have to be creating the other phases as well. That's interesting, but no. You guys good? All right. So now, guys, let's sort of tie this all together. So draw yourself a phase diagram. And guys, as you are drawing your phase diagram, label the arrows and the critical and triple point. Yeah. Obviously, this is not a phase diagram. Yes. That is true. And what we'll do is we'll compare the phase diagram with carbon dioxide in a minute. Yeah. What's who? Just a way to denote the lines, because obviously I lifted this out of the book, right? And they're identifying these as line segments. It's just a point of reference in order to say line AD represents melting and freezing, and then line AC represents sublimation and deposition, and then line AB represents boiling and condensation. No, there's no point there. It's just a reference point. But guys, do that. You'll notice that the arrows are given to, this is where you're going to take all of your notes over phase diagrams. So guys, label everything you can. Label the phases, label the arrows. And give it all you got. Is there enough light, or do you want lights back on? More? You're good? Okay. Label everything you can. Yeah, and then we'll label it all together, because this is all the notes that you're going to take. But guys, Hunter's point, I think, is probably important to mention as you're drawing these, because again, you will be, well, there's certainly the possibility that you could be sketching these on the AP test. And it is important to distinguish whether it's water or any other substance. And as Hunter pointed out, this is water, because that phase boundary between gas and liquid has a positive slope. Or did I say water? Oh gosh, sorry, not water, my bad. Not water, because it has a positive slope. But you can see that now, right? As you increase the pressure on the solid, you have to heat it more to get it to melt. So guys, this is probably foolish of me to even try to label this thing. We'll see how my pen does. I'm keeping my expectations low. So these are the things that I would label as I was doing this. First of all, I'd label the phases. What's down here at low temperature? Right, so this is solid. Then we understand that liquid is an intermediate phase. And then we've got gases over here. You'll notice here, Josh, they sort of retracted a little bit of their curvy line. Trying. So then, guys, our phases, our phase changes. Solid to liquid, we call melting. Liquid to solid, we call freezing. And then liquid to gas, we'll call vaporization or boiling. Gas to liquid, we'll call condensing. Or condensate, well, condensation is the noun. And then solid to gas is sublimation. And then the reverse is deposition. Oh, yep, there we go. It was going too well. So deposition. Sorry. What else can we label? So maybe, and I'm not trying to want to make yourself that the triple point, you've got all phases, and I knew I was pushing my luck. So you've got all phases and equilibrium. Critical point is no liquid. No matter what, up here we have a supercritical fluid. I think we've done it. Yeah. No, because it's not something that happens, it's something that doesn't happen. No, not to my knowledge. You guys all good? Oh, Eliza? A liquid. Yeah, it actually, and the only experience I have with it, like I said, is supercritical carbon dioxide, and it really does look like a liquid. You guys have a lot of stuff to Google tonight.
How exactly then is a supercritical fluid like a gas if it's
And again, my experience with them is fairly limited. It's just sort of some exotic idea, other than it decaffeinates coffee. But it in some ways, I think it actually does even fill the volume of the container and things like that. Yeah, we don't need to do a super deep. We don't need to do a super deep dive on it. It's not critical to what we're doing. So guys, allow me to offer you this as a way that we're going to wrap things up. Don't allow yourself to get sidetracked by the ethereal idea of a supercritical fluid and miss the stuff you actually need to understand. So for example, I offered these to you just by way of comparison. This is familiar. We've looked at water. This is carbon dioxide. They do actually give us the point at which this thing goes supercritical. So high pressure, 73 atmospheres. Not wacky high, but pretty high. And then 31 Celsius. So slightly above the freezing point of water, but at a pretty high pressure, 73 atmospheres, carbon dioxide goes supercritical, and you end up with that supercritical fluid. Also notice, guys, this, and this is the one that I find the most practically interesting. Notice where the triple point is for carbon dioxide. 5 atmospheres. You should be able, if you're understanding what we're talking about, to make the connection between that and the fact that dry ice exists. That would be a great question. Guys, what from this phase diagram allows you to better understand why dry ice is a thing? And again, I think you understand the idea that because we're down here at 1 atmosphere of pressure, that carbon dioxide sublimates rather than liquefies. We okay? So guys, we've got about 3 more minutes of stuff to do. My fear is that the questions that people want to ask are to run down rat trails that aren't going to get us anywhere. So if you believe that your questions are germane to what we're trying to accomplish as a group, I'd love to answer them. But if they're things that are a little more esoteric, either Google them or we can talk about them later. You okay? Yeah, go ahead.
Would it be that hard to induce 5.11 atmosphere?
Oh, so what would that be?
Because you're saying that it might be possible to do.
Well, so let's. So, what is? Gosh, I don't remember the number. Is it like 27 psi's in atmosphere? I think that's about right. So if 27 psi is in atmosphere, oh boy. So what are we looking at? 5.11? So 137 psi. I mean, I can run that in my bike tires. Yeah.
So the harder thing to do is try to get the temperature down to that. If you want to try and reduce that in lab.
Yeah, certainly.
Wait, so this is saying that like, you know, like dry ice like here, like it's at capacity up to -78 degrees Celsius or solid?
No, negative 50. Oh, yes. Oh, I'm sorry. Yes, that's right.
Dry ice like freezers like -78 degrees Celsius?
No, they're not, and that's why they have vents, because they're always off gassing. So they keep it cold so it doesn't melt as rapidly. But so maybe this, in order to collect the dry ice, you've got to have a freezer that gets down to 78.5. But they don't try to maintain it at that temperature. They just replenish their supply. There's a dry ice truck that fills them up, and they just allow it to off gas and sublimate. Does that make sense? Okay, guys, we've got a couple more things we need to do in just a minute or two left. Here's what you're going to do. Looking in chapter 12, We are not going to summarize chapter 12. But you do need to read 12.1 and 12.2 and understand, and I'm not going to give you time to write these things down, it's all in the chapter. You need to have an understanding of the difference between what are called crystalline solids and amorphous solids. Guys, A means without, morph means shape. So a crystalline solid you're familiar with, those are things like the salts. Amorphous solids are solids without shape. Think rubber. Think things that are solid, but their shape is not crystalline. You need to understand the difference. And then additionally, guys, within the types of crystalline solids, you need to have a fundamental understanding of molecular solids, which are things like sugar, covalent network solids, which are things like diamond, ionic solids, which are things like salts, and then metallic solids, which are things like the metals. So you need to be able to differentiate something that is crystalline from something that is amorphous. And then within the larger heading of crystalline solids, you need to have a fundamental idea of molecular solids, like sugar, they're held together by intermolecular forces. Covalent network solids, which are obviously held together with covalent bonds. An example would be diamond, although it's not the only one. Ionic solids, which are ionically bonded like the salts. And then metallic solids, which you can read about there. So guys, again, this is your homework. The notes are posted on our website. We have about 2 minutes left. On Wednesday, we will grade both of these assignments, and we will wrap up this unit by talking about solubility. And then, guys, test will be Friday. So I'm going to steal this really quickly.